More median spin.
Right. Thank you. Right. So today we're gonna talk about finite-dimensional median spaces. So I've been saying a lot of times, right, that one of the reasons to be interested in the median spaces is that they arise as asymptotic cones or like limits of things, and usually those spaces will be finite-dimensional. Okay, so these are like the ones that are more directly relevant to geometric group theory, or like discrete, certain kinds of groups at least. And they are much better behaved than infinite dimensional ones like one. And in many senses, like you can really treat them like some kind of cube complexes, and most results that hold in a cube complex will also hold here. And essentially, a good rule of thumb is if something is true in an artery and it's true in a cube complex, it's also going to be true in this setting. You might need to work more to prove it, but it's going to be true. Okay, so let me define dimension or rank, because there are many equivalent ways of doing this. So first of all, what is a cube? Because you do have cubes in median algebras. So the K cube is, well, the median algebra that you get as the zero skeleton of a K cube, essentially. So here's the median algebra, right? That is a product of K copies of the set with two elements, and M, the median operator, just does a majority vote on every coordinate, right? Where M takes a majority vote on each coordinate. Okay. And the second definition, I've already said it yesterday, we've seen it in Near's mini course. Let me repeat it. What does it mean that two half spaces are transverse, right? So two half spaces of a median algebra. Oh, so here I'm going to define this only for K finite, okay? Because otherwise there's a few possibilities. So let's say K is a natural number. Two half spaces are transverse if H and its complement is incomparable to K and its complement, or equivalently in terms of intersections, if the four intersections are all non-empty. So H intersect K, H star intersect K, H intersect K star, and H star intersect K star are all non-empty. So there are two definitions of rank for median algebras that use these two notions, right? So say theorem, this is due to Bowditch. So if M is a median algebra, this way, so the following are equivalent for a median algebra M and an integer R. Okay, so number one. So R is the maximum dimension of a subalgebra that is a cube. So R is the maximum K such that M contains a K cube as a subalgebra. Okay, and number two, right? So this works like in cube complexes. If you want to define the dimension of a cube complex, it's either the largest dimension of a cube or the highest cardinality of Poisson-verse hyperpole for half spaces. So R is the maximum cardinality of a pairwise transverse set of half spaces. Okay, so there is a third definition in the case that M comes from an actual median metric space. So, so if M comes, so it's the underlying subalgebra given by a connected enough yes, connected median space, let's call it X, the metric space, then this is also equivalent to 3. So R is basically the topological dimension, right? You need to be a little careful about spaces not being locally compact. So I'm going to write R is the maximum topological dimension. Some people prefer to call topological dimension Lebesgue covering dimension. It's the same thing. I mean, or at least that's what I mean here. The maximum topological dimension of a locally compact subset. Okay. And so this number, if this number exists and it's finite, that's the rank of the median space, and we say that or the median algebra, and we say that has finite rank. Right. So if such R exists, we say that it's the rank. Otherwise, we say that M has infinite rank. Okay, questions so far? So how does the proof go? I'm not going to prove this because it uses a few facts that I haven't mentioned. But I mean, the idea of the proof is quite simple, right? So showing the equivalence of 1 and 2 is kind of straightforward because, well, so first of all, if you have a K cube, let's say you have a 2 cube, so basically just a median algebra that looks like a square, it's quite standard to just like find some hash spaces of M that separate these points this way, and then they have to be transversed. And going the other way around, if you do have 2 hash spaces that, you know, 4 hash spaces that are transverse, then you just pick some points in the 4 sectors, and then you apply medians until they stabilize onto an actual subalgebra that looks like a square. So I mean, this is all quite simple. Showing the equivalence with 3 is more interesting. So one inequality is easy because, well, if you do have a K cube and you're inside a connected median space, you can fill in the cube. So you really get a subset that has at least that topological dimension that is a product. The other way around, you want to show that if this is the rank of the median space, then any topological subset has at most that dimension. So this is a bit trickier. So you can do this sort of purely topologically, because there is a different notion of dimension for topological spaces that is called separation dimension or inductive dimension. So basically, you say, okay, 0-dimensional things are because they're disconnected. 1-dimensional things are those where any 2 points can be separated by a 0-dimensional thing, and n-dimensional thing, you know, at most n-dimensional things are those where any 2 points can be separated by an at most n-1-dimensional thing, go on like that. And here in finite rank, you can really realize half spaces as connected components of some codimension 1 subset that is kind of it's itself a median subspace of lower dimension in this sense. And so proceeding this way, like you can always cut, and proceeding inductively in this way, you prove this the other inequality. Okay. So let me give you a few facts that show that somehow in finite dimension median spaces are a bit nicer. Maybe just a silly remark. So what are the low dimensional cases, right? So rank 0, a median algebra has rank 0 if and only if it's a single point. Because any 2-element subset will be a 1 cube. And a median algebra will have rank 1 if and only if it embeds in a 3. And so if you want the tree to have a metric, there are some cardinality issues, okay? But this is all an artificial problem, so let's forget about that. Okay. Let's see. So first thing that I can say about this space is the following. So say that X is just any finite rank median space now. Then 2 things are true. And essentially, So first of all, it's locally convex, right? So any points will have a neighborhood basis of convex neighborhoods. Right, this is not true for general spaces, but it is always true here. And secondly, so this is telling you that half spaces are not too bad, right? Because I mentioned this the other time, it means that you can really separate not just points by half spaces, but like really neighborhoods of points. And using this, you can show that every half space of X is either open or closed. Okay, possibly both at the same time. So of course, if it's connected, you cannot have both at the same time. But this is telling you that half spaces are really nice topological subsets, like they're not a mess. And just for comparison, so this is going to be an exercise in a few minutes, right? Instead, so in L1 of the interval, things are very different because every proper convex subset has empty interior. Subset as empty interior, and every half space is there.
Using L1 as a linear structure, so convexity means different things.
Yeah, convex for the linear number. Okay. Everybody happy? So then, yeah, another good property of finite rank median spaces. So this has been mentioned many times, but let me write it on the board. Once is that just like cube complexes and Rn, well, they have their own L1 metric, but they also have a Kazhdan metric and an injective metric that are very canonical. So this is also due to Bowditch. So let X be a, now we need complete. Well, for instance, because we've seen that all injective metric spaces are complete, right? So complete, connected, and finite rank median space. So then there are two more metrics, right? X admits a canonical, and I'll say what I mean again in a moment, a canonical zero metric. Let's call this D2, such that the identity from its own median metric to X with the zero metric is by Lipschitz. And the by Lipschitz constant only really depends on the dimension, as you would expect. And same with an injective metric, right? So X admits blah, 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 injective metric. The infinity, such that, again, the identity is by Lipschitz. So again, what's the idea of the proof? Oh yeah, what do I mean by canonical first? Well, canonical here again means it's invariant under isometries, but also really if you have a cube embedded into your median space, just in the median space it will be isometric to a cube with the L1 metric in Rn, and in each of these metrics it will become isometric to the Kazhdan metric, the Euclidean metric on that cube or the injective metric on that cube. Also in particular, right, so whenever a group acts in some way on a median space, it will also act in the same way on an injective space and on a Kazhdan space. But you do get a lot more information out of the median metric. So the proof, again, you know what you would like to do on every cube. So the strategy of proof is really just you approximate, you have 2 points, you want to sort of define what their Kazhdan distance should be. You approximate the area around them or the interval between them by finer and finer finite median algebras. Each of them corresponds to the vertex set of a Kazhdan cube complex in which you know how to define the Kazhdan metric. And so these better and better approximations give you a distance of those points, as it should be, and these distances converge to what the Kazhdan should be, and then you need to check its Atelier.
Probably you just said it when you said about canonical, but like if I do fraction by isometries,
Yeah.
then it's also given.
Yes, the whole isometric group of the median space will be embedded inside the isometric group of the Kazhdan, like naturally. Second part, you could do the same thing with cubes, but there is a more elegant argument, right? I mean, here the infinity metric will just be take your points, look at chains of half spaces that separate them, and apply the measure that we've defined yesterday, and just like the largest measure of a chain of half spaces that separates the 2 points. That's not how Bowditch does it. Bowditch does it in a much more elegant way, because it's again, you can also define this in terms of median morphism, one Lipschitz median morphism, the real time.
Wouldn't it be the envelope? The envelope?
No, this is not going to be the envelope of the L1 metric, because the L1 metric does not embed in here isometrically, right? So the injective file of X with the median metric is going to be in general a max, right? It's just going to be in infinite dimension. This is just some other metric that you define. Are you happy for
Yeah. Just that I check. So if I start with like in R2 and then do I get the obvious metric?
Yeah. On every cube inside the median space, you median is the L1, K0 is the L1, and unfitted is the unfitted.
So is there something like minimality? Like you could sorry, yeah.
Because it's really not about any,
Right.
but this is like really, it's like the good, and of course this will need finite ranks, because like, of course you have L1 spaces and L2 spaces, but these are now really different spaces. It's not different metrics on the same space. Okay, so corollary that now follows from both of these things, right? Under these assumptions, X is contractible. And Thomas just proved it for us in the injected case 2 minutes ago. But so something slightly weaker than this holds much more generally, and really much more generally. And I want to show you this because like this is my favorite proof of something that I'm going to show you today. So it's actually the only thing I'm going to prove today, but it's also my favorite. So say that Y is just a topological space with a continuous ternary map, the continuous and satisfying the first 2 axioms in the definition of median algorithm. So these were like the really simple ones. So M should be symmetric. If you permute the points, it should not vary. And M2 means if you apply M to 3 points and 2 coincide, that's the value that M takes there, right? Very basic situation. It will in particular cover all median spaces of any rank. Then I don't know if Y has to be contractible, probably not, but it certainly has to be spherical. Then Y is by which I mean, so Y is allowed to be disconnected, but all higher homotopy groups from the fundamental group onwards will vanish.
Particularly greater.
No, 1 is fine. Also, it's also true for 1. It's not true for pi 0, but it is true for pi 1. I'm gonna prove it. Then you can tell me if you're not happy with it. And this is a really simple, beautiful argument.
I think people are confused because usually a connected space with all vanishing by 1. I mean, it's EW complex, then it's
So if Y is connected and has the homotopy type of a cell complex, then this is implying contractibility. But my spaces won't in general have the homotopy type of a cell complex. Okay, proof. So say that you have a map, right, from a sphere with a base point into Y with a base point Q. Okay, so let's call this map F. Well, we can also take a product of two copies of this sphere, and here define the map. Let's call it H. So what does H do? So H of X and Y is just the median of F of X, F of Y, Q, the base point that we have there. That's an honest continuous map. And if we now here put the diagonal embedding, this commutes, right? Why does it commute? Because, well, the median of F of X Q will be F of X, okay? But now this map is actually quite special, right? Because of this N2. So there is a bunch of stuff that here is sent to a point, right? So if one of the two coordinates here is P, then here you will see Q appearing twice. So all the stuff where one of the two coordinates is P gets sent to the base point and collapses there. So this actually factors through the quotient where you identify Sn times P. Yeah, exactly. Where it is saying the right word. Right? So in here it's still a continuous map. And this is called a smash product in topology. In this case, even if you don't know what a smash product is, it's easy to see that it's just a sphere of double dimension. Because the complement in Sn cross n of this stuff is just a product of Sn minus a point cross Sn minus a point. So the complement of this stuff collapsing is really just R to the 2n. And you're doing a one-point compactification like left and left. And now it's done, right? Because now we've shown that any map from a sphere into Y actually factors through a map of the 2n sphere. And well, we know that homotopy groups of spheres below the dimension are all valid. And these are like the easy homotopy groups to compute. Right? So conclusion. Every Sn in Y factor to a map from F to N, and phi n F to N is good. Okay.
What you have to prove, right, that the map is homotopic linear, right? The map of
I mean, like you do just have like you do have more physics between both. And like the homomorphism here factors. Again, this map is not like this does not commute up to homotopy. This really commutes on the nodes, right? So the map between the homotopy groups given like this factors like through a map of the zero. Okay, so these are like some initial topological understanding of median spaces. So let's see some finer topological properties. And now, so again, I mentioned the other time, right? If you want to understand quasi-flats, for instance, in a metric space, you can usually reduce this to understanding topological flats in the asymptotic column, right? You just go to a more complicated space, but then you can use topology. So what can we say about topological flats in median spaces? Because this is going to be related to understanding quasi-flats in cube complexes, for instance. So here's a theorem of Bojich. Right, so let X be a complete finite rank median space. And suppose you have a topological flats in it. So let omega in X be a closed subset that is homeomorphic to Rn. I should say maybe to, let's say, R to the R, and let's say that here it's a complete median space with finite rank R. Okay. then, so first of all, first non-trivial fact, so omega will actually be convex in this case. Then omega is convex. And it's actually basically just going to be a cube complex. So then omega is convex and admits a locally finite decomposition into convex cuboids. So i.e. subsets isometric to just a product of integrals with the L1 method. Okay, so whenever you look at topological, whenever you find a topological plot in there metrically, it's just going to look, I don't know, I'm going to draw some picture, right? But then maybe it will have some decomposition into squares. Maybe there's more than one around the vertex, right? Sometimes, but it will sort of like metrically be some tiling of a flat by cubes. So it's only quasi-symmetric, right, to a linear flat, but it's not too bad. Maybe a word on the proof. So the proof of this, if you've seen some asymptotic cone stuff, it's kind of a standard argument. So it's like the argument that Kleiner and Dave used a long time ago to sort of study asymptotic cones of symmetric spaces and finding, describing flats there. It's also being used in asymptotic cone mapping test groups. The moral is that if the rank of the median space is R and you have an R flat, there isn't really much space for it to not be convex or do anything to it. But the proof is a bit more complicated than that. So in general, so maybe this locally finite should be a bit surprising because I said that asymptotic cones usually will be very much not locally finite, but usually these kind of non-locally compact behaviors come from some kind of branchy stuff. They tend to branch, right? But along a flat, somehow flats are sufficiently small and well-behaved that they don't go crazy when you take an asymptotic cone. I mean, this is a general thing about sort of abelian and nilpotent things that are kind of better. So corollary, you can understand quasi-flats and cube complexes. So let me state the theorem that is like Bowditch's version of this. Some slightly weaker results were due to other people earlier, and so I'll discuss that afterwards. Right, so let X be a cube complex of finite dimension. Let N, which is possibly a much smaller number than the dimension, let it be the flat rank of it. Oh, I should say cocompact. A cocompact, meaning just that the full isometry group of the cube complex acts cocompactly on it. So let N be the flat rank. So let N be the flat rank of X. So really the highest dimension of a genuinely isometrically embedded flat in it. And you can really use the Kazhdan with this actually. Then so every quasi-symmetric embedding of a flat of that dimension. So quasi-symmetric, of course, does not depend on the specific metric based on X, whether it's L1, L0, or whatever. I wanted to say something else. Oh yeah, and again, of course, you take N equal to the flat rank, but it might be much smaller than the dimension of the cube complex. So any such quasi-symmetric embedding has image a finite Haagerup distance from a finite union of portions, defined in the right way. That is, convex subcomplexes that split as a product of quasi-rings of the form L1 cross dot dot cross Ln, where n is the same. with each Li, again, a convex subcomplex quasi-symmetric array. Questions?
Yeah, so the cardinality of the finite union depends on the Ui settings.
How many orthons you mean? You're asking if the number of orthons will depend only on the Qi constant, or
no, the union. How many elements in the union?
yeah, finite union. You're asking the number of orthons.
Yes.
Yeah, the number of orthons. I mean, it will certainly depend on the space. If you fix the space and you fix the Qi constants, it might only depend on that, but I remember there were some subtleties that Brian was discussing in his paper about this, and I'm not sure what the answer is. Other questions? But the important thing is that this, like, orthons are like something very rigid that you can sort of like control, hopefully, in general, and this tells you it's quite a powerful structure theorem for quasi-flats. So, okay, so this is due to Bowditch in this case, but there is also a very strong result that is a bit less general due to Juan. So, so this is due to Juan when
You really have to say QI to array. You can't say array.
no, it doesn't. No, I mean, like, if the dimension is bigger than the flat rank, this would be higher than 1 dimension. They're just like thickened arrays. Yeah, like you could totally have like this, right? Or a ladder. And if you want them to be convex so that you can really control them, you kind of get that. Of course, like you can just say, okay, each of these is going to contain actually a unique, coarsely unique K0 line or K0 array, and then you're close to K0 orthons, but these are like way more restricted than like convex orthons.
Sorry, I got confused about the picture you drew. Like, how is that convex?
I mean, this is convex, two-dimensional.
Okay, I guess there's no rest. Like,
There is nothing else. Yeah, no, here there isn't a cube. Yeah, if there were a cube here, it wouldn't be convex, but I'm saying there isn't. No. I mean, of course, like you can ask whether a cocompact zero cube complex really contains a convex subset of this kind. But yeah. What do they want to say? Yeah. So this was shown by Juan if n happens to be the same as the dimension of x, right? So if x doesn't have big dimensions, but big dimensions for reasons unrelated to flats somehow, and this is already really very strong theorem. Like it's exactly what you would want to study quasi-isometries of RAAGs, because in Salvetti complexes the dimension of the cube complexes, the highest dimension of the flat are the same. But for instance, if you care about rectangle coxeter groups, this won't do it wrong. And it's due to Bowditch in general, right? However, if X happens to be not just an arbitrary cube complex, but an HHS, for instance, then it's also, it was known earlier. So, remark. So this corollary doesn't just hold for cube complexes, it holds for any space where the asymptotic cone is a median space in the right way. And I mentioned that there's a lot of groups that do this. So, for instance, coarse median groups, sort of the corollary holds with a very similar statement for all coarse median spaces. If you know what they are, good. Otherwise, it's okay. I mean, this is a cube complex conference, so. But for HHS, so for HHS, it's not due to Bowditch, it was known earlier, and it's due to, of course, first Hagen insists in its quasi-flat theorem. And I should say, so Juan's proof does not use asymptotic cones in any way. So his proof is based on the fixed boundary and doing stuff inside the space. So it's not like if you don't learn median spaces, you'll never be able to prove a theorem again. But they do help. And I think you guys also use asymptotic codes, right? In your
we use one theorem also.
I have a lot of time left. Okay. We might finish a bit earlier today. So how we've been discussing just topological properties essentially of median spaces. Let me say something about actions. So somehow actions might arise from if you're interested in studying automorphisms instead of quasi-isometries. And I mean, the bottom line here is that we do have quite powerful results for actions on cube complexes, but essentially they all can be proved also in median spaces, but most importantly in median algebras. In median algebras where you have an action that doesn't preserve a topology, doesn't preserve a metric, but still the same kind of results that we know for actions in cube complexes are going to hold. So actions on median spaces / median algebras. And actions on median spaces I'll assume to be by isometries, right? Actions on median algebras I'll just assume to be by median automorphisms, right? So just by bijections that preserve the median. And so as an example, if you take the real line, as a median space, the assumption group is just translations and reflections, but as a median algebra, the group of automorphisms is all homeomorphisms. So this is quite a different concept. So the first thing I want to mention is that sort of even automorphisms of median algebras are semi-simple, right? So either they fix a point or there is an axis. Okay, so let M be a finite rank median algebra. So say that you have an automorphism of the median algebra, and if you know a bit about cube complexes, you'll have seen this. It doesn't split any half spaces. Right, so there isn't a power of G, and there does not exist a half space, but that this power of G takes the half space with its complement. Then either G fixes a point, or G admits an axis. So what is an axis here? Because we don't have a metric. Well, it's a point such that its orbit only ever crosses each half space that it crosses once. Or there exists a point that the effect of half space is separating the n x from the n 1x are all parallel to each other. So in particular, if you are in a median space, then you really get an invariant geodesic. And so this is due to Haagerup for cube complexes, and I guess myself in general. So, and I want to emphasize, so here in cube complexes, we don't really need finite dimension. There is a different argument at work, but this is going to fail if you're in finite dimension. If you take an L1 space, you have parabolic isometry. And another sort of powerful theorem that one has for cube complexes that one tends to use a lot in practice is the fact that they have a core, like the Kazhdan core, which is also something one defines using the metric, but it also holds in this generality.
Sorry, Elia?
Yeah.
What did you say? So you said identity still works if you're not finite rank with the algebra.
Yeah, if it's not finite rank, it's not true in general. There are isometries of L1 things that are parabolic. So where the translation, like, okay, let me maybe say what the corollary is for median spaces so that it's clear what I mean. The corollary, if X is not complete, a geodesic median space, the geodesic median space, and G is any isometry. So now you don't need this assumption anymore, because when the median space is connected, you cannot split any half space because they're either open or closed, and they cannot be both if they're connected. Then, so either G fixes a point, or it leaves invariant a geodesic line along which it realizes the translation length. So either G is a point or G has an invariant geodesic along which it realizes the translation length, which is positive. So in infinite rank medium spaces, you have example like geometries that have zero translation length but don't fix the point. And what's kind of weird here is that this is not about completeness, right? So this is proven if the medium space is not complete. So somehow you find your fixed point without completeness, which is kind of strange. Other questions? Yes.
When you say that you're impossible, that you find a fixed point, there is an actual fixed point.
It is an actual fixed point, yes. Yeah, it's really, yeah. Okay, so let me conclude with an analog of the Capras-Seguin theorem, which I guess we won't see in. Will you do something about it? No, I guess right. So let again be a median algebra, find a rank, and say that G is a group acting on M by automorphisms, and again without inverting half spaces. And assume that G is finitely generated. Somehow this is really important, otherwise this falls. And there are minimal invariant convex subsets that are non-empty. Then there exists a minimal G invariant non-empty convex subset. And so in general, you don't have any invariant metric. So it could be that outside of this convex set, you're seeing some stretching and some contracting that stops you from having an invariant metric. But still, inside of this invariant convex set, which always exists, you will see exactly the same kind of skewering dynamics that Capras and Seguin are interested in. So, and if H is a half space of M, such that neither side contains C, such that both H and H star intersect C, then it's skewered by some element.
You said something about the metric, but I got confused because like you just have to read an algebra here.
Yeah. So there might not be an invariant metric. I mean, like you can wonder, like it might be impossible to define a metric that is invariant with respect to the group action, because it might be like that your group action is sort of like shrinking some stuff, like it's sort of like mapping bigger and bigger sets into smaller ones somehow, like into themselves, and then that means that you cannot define an invariant metric.
So if the conclusion means that G is a unique part, right?
Yeah, so any G that does that will have to be in order.
So in particular, I guess it means that like so if you're finally
finitely generated finitely generated infinite torsion groups probably have to fix a point.
Or they have to have
or they have to have space inversions. But then you can always, like when you're in finite rank, you can always get rid of the inverter. Yeah, there are things that it's not.
But that's it's interesting that this is not really a metric property. It's not really what isometries, it's just a property.
Yeah, it's quite weird because also like when you want to show that something like this, like I mean, of course you define C as an intersection of half spaces with some property, but you need to show that an intersection of half spaces is non-empty. And in general, you use some kind of compactness to do this, right? But here somehow with the finite rank assumption, you don't need to use any compactness for any kind. Okay, so maybe let me conclude with just a question, because I think this got mentioned before. So again, so the kind of actions that are most interesting in medium spaces are those that arise as limits of something and will generally be indiscrete actions. But in fact, I don't know the answer of the following. I really don't have even an indication of what the answer should be. So let's state it. Maybe somebody will think about it and let me know. The question, suppose that let a group G discrete act properly and cocompactly isometries on a finite rank medium space, then does G have a cocompact cubulation? So if the answer is yes, it's going to be very hard to prove because it will probably require some version of Rick's theory that works for things that are not RAAGs. If the answer is no, so if there is some group that is not cocompact cubulated but somehow manages to act in such a state, it's hard to imagine somehow because there would have to be some way of showing that something is not cocompact cubulated that doesn't at the same time also show that you don't act geometrically on a finite rank medium space. And I don't know any such way for the moment.
Your belief on the answer. Yes or no?
It has absolutely no idea. Like I would not. Yeah, even if somebody just I don't know. If you're under threat of death, I couldn't. I couldn't come up with what the answer should be. Yeah. So yeah, I'll stop here. Thank you.
Would you have any idea of how you could extend the list construction to more general things?
No, no, but I think it's a great question. Like I think somebody should think about it. Maybe somebody is thinking about it. I don't know. Yes.
The final theorem, if you look at all of the possible convex subsets P, then does that form some kind of product region or what?
So it doesn't need to split. If you have an invariant metric, so if you're in a median space with an invariant metric, then it will split as a product. But in general, it can consist of various disjoint connected components. So here's an example. So take a tree, and now define an isometry that fixes the zero skeleton pointwise. So it fixes the zero skeleton pointwise, but on each edge, it's just a homeomorphism with no fixed points that just pushes some way. It's not an isometry. Oh yeah, did I say isometry? I meant homeomorphism. Yeah. So it's a median automorphism. It's a homeomorphism of the tree. It just pushes, and yeah, in this case, the convex set is everything, right? Okay, I guess in this case it's not okay, but then say that maybe you have some portion, maybe it does this on every edge, but one edge is actually fixed pointwise. Then your convex set can be this, or it can be this. Or in fact, I guess your convex set should be an edge. And any edge can be your convex set. But the union of all your possible convex subsets does not split as a product. It's just a bunch of things separated by things that are fixed, but you don't need to be a product because you don't have any variant metric. It could be a vertex, yeah, but it could also, so it can be a vertex, but it can also be an open edge. Yeah, open. Yeah, you're right, open. Yeah, it can be a vertex or it can be an open. Because I'm not saying closed, because I cannot say closed, right?
Do you have some examples to keep in mind where like the action is not by isometries and we can see what the half space that's being skewed?
Like an example other than this?
Say?
An example other than this?
I was totally distracted for the first 5 minutes. Were you talking about that? Okay. So
I don't know. Like, yeah, this is an example of I can tell it. Okay, yeah, I can repeat it later.
Yeah. You can compactify it. That's an example of within algebra. And then you can just forget about the boundary and you have a.
What was your question again?
I wanted to see an example where you're acting by a group cube, not by isometries, maybe by indices or something. And I want to see what's a half space getting skewered, just to get a question.
Yeah. For that question, I think this is fine. But what we're saying, if you have any action on a Q complex, you might want to look at the action on the roller compactification. That is an action on a median algebra by median automorphism that doesn't have an invariant.
Any more questions?
can ask him in the comments.